Welcome to G Fun Facts Online. On a summer day in the year 1054, astronomers in China, Japan, and the Middle East looked up at the sky and witnessed something utterly impossible. A new star had appeared in the constellation of Taurus, blazing so brilliantly that it was visible in broad daylight for nearly a month, and it remained visible in the night sky for almost 2 years. They called it a guest star, a temporary visitor in what was supposed to be the immutable, unchanging heavens. Today, we know that these ancient stargazers were not witnessing the birth of a star, but rather the violent, catastrophic death throes of a massive stellar giant ending its life in a spectacular supernova explosion. The expanding shroud of stellar shrapnel left behind by this cataclysm is known to modern astronomy as the Crab Nebula, a sprawling, glowing web of expanding gas that spans light years across. However, the most fascinating object in this celestial graveyard is not the beautiful nebula itself, but rather the unimaginably dense, hyperactive corpse hidden at its very center. This is the Crab Pulsar. For decades, this stellar remnant has served as one of the ultimate physics laboratories in the universe, a place where matter, energy, and gravity are pushed to absolute extremes. And yet, for the past 20 years, the Crab Pulsar has harbored a baffling secret. Buried within its rhythmic radio flashes is a bizarre, highly structured signal that looks exactly like the stripes of a zebra. No other pulsar in the known universe exhibits this kind of perfectly spaced, high-contrast banded emission. For 2 decades, the zebra stripes of the Crab Pulsar defied every single theoretical model thrown at them by the greatest minds in astrophysics. But now, thanks to a stunning breakthrough in theoretical astrophysics, scientists have finally decoded the zebra pattern. The answer lies in a delicate, cosmic tug-of-war between two of the most powerful and complex forces in nature, the bizarre quantum mechanics of relativistic plasma and the space-time warping gravity of Albert Einstein's general relativity. To truly understand how this stellar barcode is generated, we must take a deep journey into the heart of a dead star, explore the strange behavior of light in extreme environments, and unravel how a celestial double-slit experiment is currently beaming its results to telescopes right here on Earth. Let us start by examining the anatomy of a monster. When a star at least 8 times as massive as our Sun exhausts the nuclear fuel in its core, the outward pressure generated by nuclear fusion suddenly stops. Without this outward pressure, the core can no longer support the crushing, astronomical weight of the star's outer layers. In a fraction of a second, the star collapses inward at a significant percentage of the speed of light. This sudden implosion triggers a massive shockwave and a rebound explosion that rips the outer layers of the star apart in a supernova. What remains behind is the star's core, compressed by gravity into a sphere scarcely 20 kilometers or 12 miles across. This is a neutron star. It is an object so profoundly dense that a single sugar cube-sized amount of its material would weigh over 1 billion tons on Earth. The extreme gravitational pressure literally forces electrons and protons to crush together and fuse, creating a solid sphere essentially composed entirely of tightly packed neutrons. But the stellar collapse does much more than just amplify density. It also hyper-amplifies the star's rotation and its magnetic field due to the laws of conservation of angular momentum and magnetic flux. Just as a figure skater spins dramatically faster by pulling their arms in toward their body, the collapsing star dramatically increases its spin rate as it shrinks from millions of kilometers wide to just 20 kilometers wide. The Crab Pulsar, born from that supernova observed in 1054, rotates at a dizzying rate of 30 times every single second. Simultaneously, the original star's magnetic field is compressed and intensified to trillions of times the strength of Earth's magnetic field. This rapidly spinning, hypermagnetic environment acts as a terrifying cosmic dynamo. It tears particles right off the surface of the neutron star and whips them around at velocities approaching the speed of light, creating a dense, swirling magnetosphere of electron-positron plasma. As these charged particles are funneled along the magnetic field lines, they emit intense beams of electromagnetic radiation. Because the magnetic axis of the pulsar is not perfectly aligned with its rotational axis, these beams sweep through space like the sweeping light of a lighthouse. If Earth happens to be in the exact path of that beam, our radio telescopes detect a brief, sharp pulse of radiation every time the star spins. Hence the name, pulsar. Usually, the radio emissions sweeping past us from pulsars are incredibly chaotic and messy. If you were to convert the radio frequencies of a typical pulsar into sound, it would sound like a blast of broad, unorganized static or white noise. If you visualized it as a rainbow, the spectrum would show a continuous, smeared blend of colors with no distinct features. But the Crab Pulsar has never been an ordinary object, and in 2007, it proved just how strange it could be. In that year, astronomers Tim Hankins and Jean Eilich pointed a high-time resolution radio telescope at the Crab Pulsar to observe its emissions in unprecedented detail. The Crab Pulsar is unique because, in addition to its main pulse, which is the primary beam of radiation, it features several other components, including a low-frequency interpulse and a highly unusual high-frequency interpulse. Hankins and Eilich focused their attention specifically on this high-frequency interpulse, examining the radio waves in the microwave frequency range between 5 and 30 GHz, which is similar to the frequencies used by modern microwave ovens and advanced telecommunications networks. Astronomers study these incredibly fast pulses using a tool called a dynamic spectrum. You can think of a dynamic spectrum as a visual waterfall graph that plots time on one axis and frequency on the other, with the brightness of the graph indicating the intensity of the radio waves. For a standard pulsar, the dynamic spectrum of a pulse looks like a solid, featureless blob of energy spreading across all frequencies simultaneously. But when Hankins and Eilich plotted the dynamic spectrum of the Crab Pulsar's high-frequency interpulse, they were absolutely stunned. Instead of a solid block of static, they saw distinct, perfectly parallel bands of intense emission separated by dark, empty gaps. The emission was heavily structured, proportional, and highly polarized. The visual representation looked exactly like the stripes of a zebra. What made these zebra stripes so incredibly baffling to the scientific community was the stark contrast between the bright bands and the dark gaps. It was not just that the signal faded slightly between the peaks, the signal vanished completely. As the researchers noted at the time, the pattern was bright band, then nothing, bright band, then nothing. If this were a rainbow, it would be as though only a few very specific, pure colors were allowed to exist, separated by thick bands of absolute, pitch-black darkness. For over 15 years, this enigma stood as one of the great unsolved mysteries of radio astronomy. Why would a chaotic, violently rotating soup of plasma emit perfectly ordered, discrete frequency bands? Some theorists propose that the stripes were caused by a cyclotron maser, a process where electrons spiraling around magnetic field lines amplify specific frequencies. Others suggested the stripes were standing waves in the pulsar's plasma, or perhaps analogies to the zebra patterns sometimes seen in the radio bursts of our own sun. However, all of these traditional models eventually broke down under scrutiny. They either required exotic, physically impossible plasma structures that completely contradicted standard models of neutron stars, or they completely failed to account for the most striking feature of the stripes, which was the absolute darkness between them. The incredibly high contrast of the zebra pattern demanded a mechanism that could not only generate bright bands of radio waves, but also perfectly erase the radio waves at the specific frequencies in between. The first major crack in this decades-old mystery finally came in 2024, courtesy of Mikhail Medvedev, a theoretical astrophysicist at the University of Kansas. Medvedev realized that previous attempts to explain the zebra stripes were approaching the problem using entirely the wrong framework of physics. Most earlier models relied on geometrical optics, which is the idea that light travels in straight lines like bullets or simple rays. In geometrical optics, if an object blocks a light source, it casts a sharp, dark shadow. But light is not just a particle, it is a wave. And when dealing with waves, geometrical optics is completely insufficient. You have to use wave optics. As Medvedev explained, if you have a screen and an electromagnetic wave passes by, the wave does not just propagate straight through. Waves bend around obstacles and interfere with each other, creating a sequence of bright and dim fringes due to constructive and destructive interference. Medvedev proposed that the pulsar's own magnetosphere, that swirling cloud of electron-positron plasma surrounding the neutron star, was acting as a giant, frequency-dependent diffraction screen. When the high-frequency radio waves are generated deep within the pulsar's magnetosphere, they do not just shoot straight out into empty space. They have to travel through the dense, highly magnetized plasma. Because plasma interacts strongly with electromagnetic waves, different frequencies of light are bent, refracted, and diffracted by the plasma in different ways. Medvedev's 2024 mathematical models showed that this diffraction effect could indeed carve the broadband radio emission into discrete, proportional bands. His wave optics model elegantly explained the band spacing, the high polarization, and the constant position angle of the emissions, which were all factors that had tripped up every previous theory. He even proposed that two other mysterious signals observed in the Crab Pulsar, known as high-frequency components 1 and 2, were simply reflections of this same diffracted signal bouncing off the magnetosphere. It was a monumental leap forward, largely solving the fundamental mechanism of the banding. However, one crucial, nagging flaw remained in the theory. While Medvedev's 2024 plasma diffraction model could reproduce the stripes, it could not reproduce the observed contrast. The math showed dimming between the bright bands, but the real-world observations from 2007 showed absolute complete darkness. The plasma alone was simply not enough to perfectly cancel out the light in the dark gaps. Something massive was missing from the equation. Fast forward to March 2026, when Medvedev published a refined theory that finally placed the last piece of the puzzle into the board. The missing ingredient, it turned out, was Albert Einstein. For decades, astronomers studying pulsar emissions had largely ignored the gravitational effects of the neutron star itself, treating the emission process purely as a problem of plasma physics and electromagnetism. But a neutron star is one of the densest objects in the universe. Its gravity is so immense that it severely warps the fabric of space-time around it. Light traveling near a massive object does not travel in a straight line. Its path is physically bent by the curvature of space-time itself, a phenomenon known as gravitational lensing. Medvedev realized that the light escaping the Crab Pulsar was subject to two wildly powerful, yet completely opposing, forces. On one side is the pulsar's magnetospheric plasma. In the realm of optics, plasma acts as a diverging or defocusing lens. It forces light rays to spread outward, pushing them away from each other as they travel through it. On the other side is the neutron star's extreme gravity. Gravity acts as a converging or focusing lens. It pulls the light rays inward, bending them back toward the star. The combination of a defocusing magnetospheric plasma and a focusing gravity create in-phase and out-of-phase interference bands of radio wave intensity that appear exactly as the Crab Pulsar's zebra stripes. This cosmic tug-of-war between gravity and plasma alters the geometry of the light's escape route. Because the plasma is pushing the light out while gravity is pulling it in, the light rays are forced into taking multiple, distinct pathways through the warped space-time to reach an observer on Earth. By symmetry, there are at least two such distinct paths for the light. And it is the existence of these two nearly identical paths that finally solves the mystery of the absolute darkness between the stripes. To fully grasp why two paths of light create high-contrast stripes, we have to look back to one of the most famous and foundational physics experiments in history, Thomas Young's double-slit experiment. If you shine a coherent beam of light at a barrier with two tiny slits in it, the light waves passing through the slits spread out and overlap on a screen placed behind the barrier. Where the peaks of the waves from the left slit meet the peaks of the waves from the right slit, they add together, creating a bright stripe, which physicists call constructive interference. But where a peak from one slit meets a trough from the other slit, they cancel each other out completely, leaving pure darkness, which is known as destructive interference. By forcing the radio waves to take two nearly identical paths around the neutron star, the combination of gravity and plasma effectively turns the entire Crab Pulsar into a giant cosmic double-slit experiment. When two nearly identical paths bring light to the observer, they form a natural interferometer. The signals combine. At some frequencies, they reinforce each other in phase, producing bright bands. At other frequencies, they cancel out of phase, producing absolute darkness. That is the essence of the interference pattern. This is why the dark gaps are so perfectly black. It is not that the pulsar stops emitting light at those specific frequencies. Rather, The light traveling along path A perfectly cancels out the light traveling along path B by the exact moment it reaches Earth's telescopes. Because the interference is dictated by the wavelength and frequency of the light, the constructive and destructive zones alternate mathematically, generating the precisely spaced, highly contrasted zebra stripes across the dynamic spectrum. The inclusion of general relativity was the ultimate masterstroke. The previous plasma-only model was akin to having a single wave diffracting around an obstacle, which only causes soft fading and blurry shadows. The inclusion of intense gravity introduced the second distinct pathway, turning the stellar system into a true interferometer, which results in mathematically perfect cancellation and the sharp, high-contrast blackness observed by Hankins and Eilek nearly 2 decades ago. Now, you might be wondering why this matters so much. The resolution of the zebra stripe mystery is much more than just tying up a loose end in observational astronomy. The synthesis of wave optics, plasma physics, and general relativity provides astrophysicists with an incredibly powerful new tool. Because the exact spacing and contrast of the zebra stripes depend heavily on the density of the plasma and the strength of the gravitational field, scientists can effectively reverse engineer the interference pattern to map the unseen environment around the pulsar. Think of it like a medical CT scan. In medical science, tomography uses waves to map the inside of a human body without cutting it open. Medvedev's model enables space-resolved tomography of the pulsar magnetosphere. By closely analyzing the zebra stripes, researchers have already been able to deduce the radial plasma density profile of the Crab Pulsar directly from observational data, finding that the electron density drops off proportionally to the inverse cube of the distance from the star. This provides incredible, real-world confirmation for theoretical models of how pulsar magnetospheres are structured, something we previously could only guess at with computer simulations. Furthermore, this represents the very first real-world observation where gravitational lensing and plasma delensing are acting together in such a delicate, observable balance. It opens an entirely new window to investigate gravity in the strong field regime directly near the surface of a neutron star. While gravitational lensing is routinely observed around supermassive black holes and massive galaxy clusters, witnessing it interact so intimately with dense quantum plasma on a stellar scale is entirely unprecedented in the history of astronomy. The discovery also allows astrophysicists to make testable predictions for the future. The mathematical models predict that at much higher frequencies, specifically when the separation between the light paths becomes smaller than the physical size of the pulsar itself, the zebra pattern should fundamentally change its trend. The frequency where this shift occurs is predicted to lie between 42 and 650 GHz. This is well within the observational capabilities of state-of-the-art terrestrial radio telescope arrays operating today, like the Atacama Large Millimeter Submillimeter Array, known as ALMA, and the Submillimeter Array. Observing this shift would serve as the ultimate confirmation of the gravity-plasma tug-of-war theory, and provide precise measurements of the neutron star's physical radius, which is a holy grail in astrophysics that dictates the equation of state for ultra-dense matter. Finally, solving the strange emission mechanics of the Crab Pulsar may hold the vital key to understanding other transient radio phenomena in the deep, distant universe. Fast radio bursts, for example, are highly energetic, millisecond duration flashes of radio waves that originate from galaxies billions of light-years away. Many theorists suspect that highly magnetized neutron stars, known as magnetars, are the engines behind these mysterious fast radio bursts. By understanding exactly how extreme gravity and dense plasma shape the radio emissions of our local Crab Pulsar, astronomers are now far better equipped to decode the strange, structured signals arriving from the very edge of the observable universe. Science often advances not through the discovery of entirely new forces, but by recognizing how the fundamental forces we already know interact in beautifully unexpected ways. For 20 years, the zebra stripes of the Crab Pulsar were an anomaly, a stubborn glitch in the data that refused to conform to our understanding of the universe. Yet, by looking at the problem through the dual lenses of Einstein's macroscopic gravity and the microscopic wave mechanics of quantum plasma, the anomaly was transformed into perfect clarity. The absolute darkness between the bright radio bands is not a void, nor is it an absence of energy. It is the invisible signature of space and time bending around a crushed stellar core, forcing light waves to perfectly erase one another in a glorious cosmic symphony of destructive interference. Nearly 1,000 years ago, ancient stargazers watched a star die in a brilliant flash of light that outshone the moon. Today, from the heart of that ancient debris, the ghost of that star is still whispering to us, utilizing the very fabric of space-time to send a perfectly striped signal across the void. And after all this time, we have finally learned how to read it. Thank you for tuning in to G Fun Facts Online. Keep looking up, and never stop wondering about the mysteries hidden in the dark.